Cisco Certified Network Associate Day 45. Welcome back everyone, I'm Imran, your trainer for this entire series. Today we're going to talk about OSPF configurations. So if you have not watched day 44, which is the first day we started OSPF, I would recommend you go watch day 44 and then come back. But if you are just joining us for this series, then I would recommend that you start from day 1, where we start from absolute beginner. So if you are absolutely beginning into the world of Cisco Ccna, please feel free to start there, because we touch absolutely simple topics before we build our knowledge to reach where we have reached today. So the day 1 would be your ideal video to start this series, and every video is available for free on YouTube. You just have to go to YouTube and /networking inc, like the one you see on the bottom right hand corner of the screen. So without wasting much time, let's get straight into today's class. And like always, before we go ahead, click on that subscribe button and don't forget to click on the bell icon. Now what the bell icon would do is notify you when we add a new video. Also click on that like button, which would definitely make me happy, and it would promote our video so that more people can watch. Our social media contacts on this page. On the left you have our company contacts, on the right you have my personal social media contacts, and also my email address is listed there for people who really want to contact me. But I would suggest the best way to reach us is to comment below this video with whatever questions you have from this video, and one of our team would get in touch with you and help you. And also there are wonderful co-learners who help you. So even if we don't reach you, I'm sure you would get the answer for your questions by just commenting on the section below. So what are we going to learn in today's video? In the last video, we did 2.4, right? So 2.4 is configure, verify and troubleshoot single area and multi-area OSPF version 2 for IP version 4. Now, in the last video, we looked at the theory part of OSPF. So we explained in a very simple terms how OSPF works and what are the different processes and what are the different steps it takes to form a neighborship, and then how the calculation for a routing table is done. Now that was very high level working of OSPF. What we're going to look at in this video is we're going to look at few more theory that we did not touch in the last video, and we'll get straight into packet tracer and we will configure a topology. So without wasting much time, let's start. So like we said, OSPF in shared medium, this is something that we briefly touched in the last video. So I thought because I did not have a slide for it, I explained by drawing, but I thought it would make a little more sense if I made a proper slide and explained the same concept to you. So that's what we would be touching, the very first thing. After that, we would definitely get into configuration. So we would show you how to configure a topology in packet tracer, and then we'll verify. Now, a shared medium, when I say a shared medium, we typically refer to Ethernet, right? There is a switch and 4 routers are connected. Like in this example, 4 routers are connected to this single switch. It's a broadcast medium. So whatever traffic that's part in this area, that's a broadcast, right? So whatever update route 1 sends, everybody can hear, obviously, because that's a shared medium and everybody is participating in OSPF. So they're all listening to the multicast address. Now, that's difficult. I mean, that's difficult because there would be so much traffic on this network, and most of them would be unwanted traffic because everybody is listening to everybody else. So if each device were allowed to form neighborship with each other, that is a very inefficient way to do it, and that's going to break the network. It's going to be too much of bandwidth wastage. A better way of doing it is how OSPF solves the problem. In this broadcast domain, one of the router becomes a DR, a designated router, and the second best router becomes the backup designated router. Now, when you say the second best or first best, there should be an election, right? Yes, there is an election for DR and BDR, and the parameter for election is the first is OSPF Process ID, right? What is process ID? We'll talk about what process ID is, but we need to understand, if you remember in the last video, I showed few parameters in the hello that should match before you can form a neighbor, and OSPF process ID was not one among them. That means in router 1, I can create an OSPF process with a process ID of 1, and router 2, I could create an OSPF with process ID 2 in router 2, yet they will become a neighbor because OSPF process ID is locally significant. OSPF router 1 can have an OSPF with process ID 1, router 2 could have an OSPF with process ID 2, right? So if these two routers are competing for DR, obviously OSPF with a process ID 2 would get preference and they would become a DR, right? In most cases, OSPF process IDs, unless you change, most of the time it is going to be the same. If that happens, then it needs to look at the second parameter. The second parameter is the router ID, right? Whoever has got the highest router ID becomes the DR, and the second best becomes BDR. Now, the reason BDR is there is because the role of a DR is very, very important, right? Like we will be looking in the next slide. But DR is so important in this concept, that's why a second device is there to take over in case your DR fails. So if DR fails, BDR immediately switches over, becomes DR, and another election takes place, right? In the first case, when DR and BDR is elected, it's the same election. The first place or the most, depending on the election, one winner becomes a DR, the second best device becomes BDR. That's it, no more election, the single election. But once DR fails, they don't use the old data, the third person does not become the DR, a new election is taking place among all the remaining devices, and the best among that would become the BDR. Like for instance, if router 4 in this case failed, router 3 would become DR, and let's assume router 4 immediately comes back to the election, right? And among these three devices, router 4 is the best one. This becomes the BDR, right? So an election takes place. Now, typically, if the router actually fails, as in if it goes off and it's rebooting, it wouldn't come back before the BDR election happens. So it would ideally be between these two devices. But I just wanted to show you an example that what happens if there is this router, or in case there is another router better than this DR, right? Better than this DR, which was a BDR, now it's DR. But if there is something better than that DR will actually become a BDR. You understand? So that's what I want to tell you. So even if this device, let's say the router 4, which was the original DR, is back, it's not going to give, now router 3 is not going to give that role back to that device and say, oh, you know, I was BDR, you were DR, so you're back now, take this. No, it's going to be DR forever now until it fails, right? So it is not preemptively, it is not going to give up its DR. Once it's DR, right? Now, we spoke about full adjacency, right? Now, full adjacency is if it's BDR and DR, like in this medium, in a shared medium, the relationship between a DR and all the devices is always going to be full, right? We spoke about full. It's always going to be full. And if you do the verification command, which we will be doing when we configure, you would see what the other device is. So in this case, I think this is wrong. This should have been BDR. Okay. So we're talking with respect to router 4. From router 4, this is BDR. So it says full BDR, full DR other, because this router is known as DR other because it's not DR or BDR. So it's DR other. In this case, router 2 is also DR other, right? So these are in full. As we see, all of them are full. Similarly, if you're looking at it from router 3's perspective, this is right. It's full and the other device is a DR. It's full, the other device is a DR other. It's full, the other device is DR other. If you look at it from router 2's perspective, right, this is full Now this is wrong again. It should be full DR because that's a DR device that it's connected to. And this is also wrong. This should be BDR. I'm so sorry. I'm so sorry. Just made these slides. It's already 2 a.m. But I just do not want this week to go without a video. So yeah, I just wanted to put. So excuse my errors on screen. But yeah, so this device would be a full connection, but with BDR. And this is what was important. We spoke about two-way. So the device between two non-DR or BDR devices is always going to be two-way. So it's going to be two-way, and it says two-way DR other, right? Because it's a DR other, right? If it's a BDR or DR that it's connecting to, it will always be full. But if two devices between two non-BDR or DR device will always be a two-way connection, right? It will stay two-way. Now what that means is, if something fails, and if let's say router 2 becomes BDR, all the parameters are matching. Remember in our previous video we spoke, if it's two-way, that means everything that has to match has matched. It's just that they have not exchanged LSAs, right? So they're ready. If at all router 2 has to become BDR or DR for some instance, this could immediately become full, right? All they have to do is now start exchanging LSAs. All the other parameters to become a route neighbor has been met. Similarly, if you're looking at it from router 1's perspective, the same thing. This is going to be two-way, this is going to be DR, this is going to be BDR, right? So this is what the neighborship is going to be. So in effect, what happens is all the device is going to, like I said, your DR is the most important device. So LSA exchange happens, let's say all the devices sends the LSAs. If they have to do any LSA, it would send to the DR, and then DR would update in effect would update to other devices. More like point-to-point network between these three devices to router 4, which is the DR, right? So this is how they avoid creating more unnecessary bandwidth in a shared medium. Now OSPF has 3 databases and tables. So it creates an adjacency database, right? Adjacency database. Now, these are databases that you're not really going to do much. These are databases that you need to know for knowledge sake. And I don't think so. You don't even need to go at this level for CCNA, right? This is more like CCNP level topic, but still just know that OSPF has 3 databases. So there is an adjacency database. Adjacency database is a database from which a neighbor table. So if you do show IP OSPF neighbor, the neighbor table is derived from adjacency database. Similarly, you have an LSDB we looked at last time. So the topology table, right? Again, topology table is the command for checking. The topology table does not even work in Packet Tracer. So honestly, you don't really have to do all this, but just to know there is a link state database, and the topology table is derived from the link state database, right? And then there is another database called forwarding database. The routing table is derived from the forwarding database, right? So these are the 3 tables that you need to know: the neighbor table, topology table, and routing table. And the databases are adjacency database, link state database, and forwarding database. So let's look at configuration. Now configuration, it's straightforward. If you remember RIP when we did, the keyword for any routing protocol is router. Any dynamic routing protocol starts with router. So router RIP we did. Now this is router OSPF. And when we do EIGRP, it will be router EIGRP. So the format is, you say router, and that this is in global config mode. You say router, and then you give the keyword OSPF, that's the keyword, and you need to give a process ID. It's a number. So you just put an OSPF process ID. Once you do that, we go into a router subcommand. There we need to put, just like in RIP we gave the keyword network, that's again a keyword. And then we give the network ID. In RIP, we gave classful network ID. So if we gave 10.0.0.0, and then we gave the subnet mask, right? Similarly here, you do the same thing. You give the network ID, but the difference here is you don't give a subnet mask. Instead, you use a wildcard mask, right? So you do network and then you give the network ID, you give wildcard mask, and then you give a keyword called area, and then you need to give an area number. Now, since we are still working on single area OSPF, this has to always be a 0, right? A 0, because 0 is the backbone area, and every OSPF, if it's single area, has to be area 0. If you have multi-area, one of them will have to be area 0, and then you could have many other areas. But all those areas will have to be connected back to area 0 because that's the backbone area. So now let's configure a small configuration like you see on the screen on Packet Tracer, and let's see how it works. So I have not done much. I have, sorry. All right, let's go to this one. So I've just configured the interfaces. So I've just put 192.168.1.2 and 222, and each of these interfaces 192.168.1.1, 1.2, 1.3 and 1.4, and router 1 has a loopback interface of 1.1.1.1.1, router 2 has 2.2.2.2, router 3 has 3.3.3.3, and router 4 has loopback interface of 4.4.4. So because of the loopback interfaces, each of these routers take that IP address as their router ID. So this becomes router ID of 1.1.1.1, right? And similarly, all the others. So let's quickly go. This is still doing that. So let's go to router 2 and start with router 2, config terminal. So how did we do for RIP? If you remember, router RIP, right? So OSPF also similar thing. It says router OSPF. After that, we need to put a process ID. Process ID goes any number from 1 to 65,535. So let's do router OSPF 1, and we give a network command, network 192.168.1.0. We're giving the network 0.0.0.255, right? After you do that, you need to give an area, and since we are doing single area, and as you know, every OSPF route has to have area 0 because that's the backbone area, right? If I had multiple area, I need to have one area as 0, and we could have some other area as well. But since this is single area, it has to be area 0. We also should advertise the loopback. So network 2.2.2.2. Now, in the previous case, we gave a network. That's why we did 0.0.0.25. That means wherever 0, we're telling the device that match all the networks, or rather all the interfaces, which has an IP address, compare wherever 0 is. So 192.168.1, right? All the interface that has these 3 octets matching will have OSPF running. That's what it says. And this network, like if you had more than one interface with the same 192.168.1 dot something else, right, slash maybe 25, whatever, it would still get into OSPF process. Now let's advertise the loopback. So we say 0.0.0.0. That means we're telling match all the octet, all the 4 octets, and area 0. That's it. Go back to 1. I think 1 should be ready now. So enter, configure terminal, router OSPF 1, and network 192.168.1.0, 0.0.0.255, area 0. The loopback, network 1.1.1.1, 0.0.0.0, area 0. Okay. Now, since we are starting from router 2, router 1, when everything is configured, because the election would have already happened and router 2 would have already taken the DR and router 1 would be BDR. So we will do something if you want to change it. Configure terminal, router OSPF 1, network 192.168.1.0.0.0.0 area 0, and then loop back is 3.3.3.3 0.0.0.0 area 0. Okay, and the same thing goes to router 4, configure T router OSPF 1 network 192.168.1.0 0.0.0.255 area 0, network 4.4.4.4 0.0.0.0 area 0. Okay, we have done what we had to do. Now let's go here, show IP route. Let's see if the route is injected. We can see that they have learned two routes, that's for 2 and 3. 4 is, I think it's still not. Let's see what happens to the neighborship. Show IP OSPF neighbor, right? We see that 2 has, okay, so this is with router 1. Router 1, it says the neighbor 2.2.2. This is the neighbor's router ID. So it says with 2.2.2, it is on a full state, and the router 2 is the DR. This is the dead timer. So every 30 seconds, if it reaches 30 seconds, I think it, yeah, if the number comes to 30 seconds, if you see 34, 33, 32, every time it comes to 30, it resets that number. Okay, right, yeah. So we see that the first router 2 has gone to 30. If you see here, it went to 30 and they reset it to 39, right? So every 10 seconds, it resets. So it's 4 times the hello timer. So if the hello doesn't come, if the hello, every 10 seconds, there's a hello timer that comes. So every time there's a hello, the dead timer resets to 40, right? So we see that 3.3.3 is BDR. So 2 is become the DR and 3 become, router 3 is become BDR, and router 4 is in two-way state and it's in DR other, right? So let's look at the routing table. So it says show IP route. Still, if you see, even though it's reached a two-way state here, this is not advertising. Let's see what's happening. Show IP route. And for some reason, let's see this show IP OSPF neighbors. Okay. So it's still in Xstart. It's stuck in Xstart. So what we could do is we could do clear IP OSPF process. So, okay, sorry. Clear IP OSPF process. Yes. I'm going to do that to router 3 as well. Clear IP OSPF process. Yes. And let me do the same thing here. Clear IP OSPF process. Yes. And same thing. So what it does is it just clears the process and restarts it. Clear IP OSPF process. Yes. Now let's see what happens. Show IP OSPF neighbors. OSPF neighbors. Okay. We see now, if you see there's no DR mentioned, that means router 4, because anyway it had to be, router 4 had to be the DR according to our configuration because it had the highest router ID. But because in the earlier case, router 4 was the last one to start, it did not become. Now because I reset it in such a way, I reset this first. So by the time it came, it was only 1, and then by the time the second device came, it did an election and he became the DR. And if all 4 devices come election, now router 4 is going to win the election. So he's become the DR. Router 3 is BDR, and two other devices are in DR other state. So now let's show IP route. We see that router 4 has learned 1, 2, 3, and 4 is connected. So it learned 3 new routes. So same thing, show IP OSPF neighbors. We see that everything is 3 is BDR, 4 is DR, and 2 other with 2, right? Show IP route. Okay, so it has learned 1, 2, 3. That's 2, 3, and 4 networks it has learned. So this is very simple configuration and verification. If you go back to our slide, this is the verification. Show IP OSPF neighbor. It will show if the neighborship is being formed. And one of the troubleshooting is if at all you see that neighborship is being formed and everything has gone into full or two-way state and still routing tables are not getting updated, best thing is to clear the OSPF process and it will come back and start exchanging all over again, right? So that is all for this video. We will be looking at a little more concepts in the next video, and then we'll get into troubleshooting of OSPF. So we're still going to be in OSPF in the next video. We will also look at multi-area OSPF in the next video. I think that's about the next video, and then we will take IP OSPF of version 3 for IPv6 in a later part in the series, right? So thank you so much. We'll be back very, very soon. Bye-bye.